Welcome to Auto 155, Electricity and Electronics 1. My name is Tony DeBlasi, and in this lecture I will be covering batteries. This is part 1 of a two-part lecture based on Chapter 50 from the Automotive Technology, Principles, Diagnosis, and Service, 6th edition. For additional information on this topic, please read this chapter and refer to the PowerPoint found in the course content folder. Please note that there are both audio and visual lecture attendance codes scattered throughout this lecture. Please write these codes down as you see and hear them. At the completion of this lecture, you will be required to go to the assignment folder and take the online lecture attendance quiz in order to get credit for attending this lecture. The following is an overview of the objectives covered in this lecture. I will describe the construction of an automotive battery. I will describe how a battery works. I will discuss how charge indicators work. I will discuss valve-regulated batteries and outline the battery performance factors that are tied directly to the causes of battery failure. And I will discuss battery ratings and battery sizes. The information found in this chapter will help you prepare for the ASE Electrical and Electronic Systems A6 Certification Test Content Area B. The primary purpose of an automotive battery is to provide a source of electrical power for starting and electrical demands that exceed alternator output. Batteries are very important because they also act as a stabilizer for the entire electrical system. So in other words, they are a capacitor. They help to smooth out the erratic AC signal that can be produced by an alternator. With regard to battery construction, the case, which is the container for the cells and acid, is typically constructed of polypropylene, which is a thin and strong lightweight plastic, typically around 8/100ths of an inch. The cells inside of this case contain positive and negative plates, which are constructed on a framework or a grid, which is initially and primarily made of lead. The positive plates have a lead dioxide or lead peroxide pasting placed onto the grid framework. The negative plates are also pasted, but instead of being pasted with lead dioxide or lead peroxide, they're pasted with pure porous lead. Separators are non-conducting insulators, which allow room for the reaction of the acid with both plate materials. They are ribbed usually on one side and they are porous, and they can also be an envelope that contains one of the plates. Cells typically have around 9 total plates per cell. That would be 4 positive plates and usually 5 negative plates. So they usually add 1 extra negative plate, making the average battery plate count 4 positive and 5 negative. With 9 plates per cell and 6 total cells, this would equal 54 plates per battery. Some heavier duty batteries will increase the count by 1, meaning 5 positive and 6 negative. So that would make it 11 plates per cell or 66 plates versus the 54. Whether you have 66 plates or 54 plates, the voltage will remain the same. However, the CCAs will increase. So in other words, the amount of amperage output or the potential for current would increase. So I'd like to take a moment and provide a quick recap of how a battery is constructed. What you see here in this example is a plate or a grid. Under both a positive and a negative plate exists a lead framework. Usually they add antimony or calcium to this framework to give it some strength. So in the top example, this would be my positive plate, and in the lower example, that would be my negative plate. As you can see, they are both identical right now. We're going to change their characteristic and make them dissimilar by pasting them. So the positive plate gets pasted with lead dioxide, while the negative plate is pasted with a porous sponge lead. This makes them different, or in other words, dissimilar. We then take our polypropylene case, which will be our container, otherwise known as a cell. And in this example, I'm just going to use the 2 plates. I'm not going to use the 4 positive and 5 negative or 5 positive and 6 negative. I'm just going to use 2 plates. On one side of the cell goes our positive plate, that's known as the anode. And on the other side of the cell, that would be my negative plate, otherwise known as the cathode. We cannot allow these 2 plates to touch, so we have to put a porous envelope separator between them. And it's porous to allow fluid transfer, but we don't want to allow the 2 dissimilar metals to touch. We're then going to fill the cell up, or the container up, with distilled water. And then we're going to add a mixture of sulfuric acid to this distilled water. And to be specific, it is on average between 35% sulfuric acid and 65% distilled water. You may see other figures where it says 34% sulfuric acid and 66% distilled water. This is a rough average. Once we add the distilled water and the sulfuric acid, which is also referred to as electrolyte, we then put a charge to the anode and cathode, and a typical automotive car battery cell can contain 2.1 volts. There are going to be 6 cells in the battery to give us an overall voltage of 12.6. We'll get to that a little bit later. So let's talk about how battery discharge occurs. So as the battery is discharged, in other words, current flows from the positive anode out through the system and back into the negative cathode, the sulfur inside of the battery is going to cling to the plates. And as it clings to the plates, we refer to this process as sulfation. Our ratio of 35-65 will change. So let's watch as that happens. The sulfur is clinging to the plates, leaving us with more distilled water and less sulfuric acid. Couple things to talk about with this transfer. Because we have more water and less acid, the water is more susceptible to temperature. If this battery were to get really, really cold, well below freezing, the water could freeze. And if it freezes, it will expand. This expansion can damage the case and warp the plates. It also inadvertently creates little pockets of hydrogen, which create a bigger risk or a bigger hazard of a potential explosion. So if you ever suspect a battery is frozen because it's swollen, you should never attempt to recharge it or to jumpstart it. The correct course of action would be to replace it. Notice how the battery is discharged. If we check the voltage per cell, in this case it's 1.2 volts, as opposed to what it should be, 2.1 volts. If this were the same across the entire battery, if each cell was 1.2 volts, that would be a 7.2 voltage. So that would be well under discharged or totally discharged. The other piece to mention about temperature is that if it gets too warm or too hot, the water could evaporate, leaving us with less distilled water in the battery. So when we were to recharge the battery, the acid couldn't fall back into the solution again for recharge, and that would cause the plates to corrode prematurely and cause battery failure. Now, to recharge the battery, we would simply apply a voltage greater than the battery, and the sulfur atoms that are sticking on the plates in the sulfated mode would then fall back into the solution again, mixing back with the electrolyte, giving us our 65% distilled water, 35% sulfuric acid solution. And this battery would then be recharged. As you can see at the bottom, we have our 2.1 volts. Now, as far as vibration goes, if a battery is not secured properly to the vehicle, and let's say the battery was discharged and recharged, so the plates were heavily sulfated, which will cause them to corrode and become more brittle, you can have plate deterioration, which is normal over the course of the life of the battery. In this example, you're going to see the plate break apart. It's going to start to break and fall to the bottom of the case. And this plate debris can inadvertently touch and then short out the cell. What I'd like to do now is show you a short little video that I took years ago of a battery that I had taken apart and cut into. Now, to give you a little backstory on this battery was in a vehicle earlier this day, and it was starting and running the vehicle fine. One of our customers had decided they wanted to replace the battery as a preventative maintenance because it had hit the later part of the 3 years and they were coming into winter, and they just wanted a fresh battery installed in their vehicle. So we installed the battery and took the old one back as a core. But instead of putting it in the core pile, I wanted to do an experiment and actually cut in to take a look at the condition of the plates. And what you see here is a plate from a 3-year-old battery. This is one of the positive plates, and it looks damaged along the top because I had to bend it and kind of break it out of the case. But I want to play this video to show you just how delicate these plates are. So here is the example of the plate. It's on a white piece of paper and I've got gloves on. And I pick it up in my hand and I barely put any pressure on this and it crumbles in my hand like a graham cracker. It's very, very delicate. The reason I wanted you to see this video is to show you just how delicate these plates are and to really express to you that a battery needs to be secured with its hold down bracket, holding it in place during travel. In the course of your career, you may encounter vehicles that don't have adequate hold down. You need to make sure that that gets fixed or that battery will fail prematurely. Chapter 50, lecture code question number 2. Please write this down. 115544. Once again, that's 115544. Please write this down. Figure 50.1 shows a pretty decent cutaway of an automotive battery and how the plates fit into the cells, how they overlap. Here's an actual grid in figure 50.2. This could be either a positive or a negative plate before they are pasted. In figure 50.3, It shows how the plates load together, where you have a negative plate, an envelope separator, then a positive plate, then an envelope separator, and then a negative plate, and so on and so forth. This process repeats through every cell of the battery. In figure 50.4, this actual cutaway of a battery shows the connections of the cells to each other through the partition. Chapter 50, Lecture Code Question Number 3. Please write this down. 786512. Once again, that is 786512. Please write this down. We're going to discuss specific gravity and what it means. The definition of specific gravity is the ratio of the weight of a given volume of a liquid to the weight of an equal volume of water. In other words, the more dense a liquid is, the higher its specific gravity. Pure water is the basis for this measurement and is given a specific gravity of 1 at 80 degrees Fahrenheit. Pure sulfuric acid has a specific gravity of 1.835. And as I stated already, the correct concentration of water and sulfuric acid in the battery is referred to as electrolyte. The Haldeman book states 64% water, 36% acid. I've seen it 70-30, I've seen it 65-35, but either way, a 1.260 to a 1.280 at 80 degrees Fahrenheit specific gravity is a fully charged, properly mixed electrolyte solution. We will discuss the charge indicators that are built directly onto many different automotive batteries. That indicator is simply just a small ball-type hydrometer that is installed on one cell of 6. It's not very good for testing a battery, but it kind of gives you an overall look at the electrolyte condition of one cell, and from that point you could probably extrapolate or guess what the other cells would probably be like. However, it does not accurately reflect the condition of the other cells and should never be used in place of testing a battery. We'll provide an example of how to interpret this in a bit. When reading specific gravity, you have to apply adjusted specific gravity readings based on the temperature. Temperature correction is needed because specific gravity changes with temperature. Cold thickens the electrolyte and raises the specific gravity. Heat thins the electrolyte and lowers the specific gravity. Hydrometers are calibrated at 80 degrees Fahrenheit. Electrolyte temperatures above or below 80 degrees must be adjusted. For every 10 degrees Fahrenheit increment below 80 degrees Fahrenheit, subtract 0.004 to the hydrometer readings. And for each 10 degrees increment above 80 degrees Fahrenheit, you would add 0.004 to the readings. Here are a couple of examples. In this case, we have a hydrometer reading of 1.250, but the temperature of the electrolyte is 40 degrees Fahrenheit. We would need to subtract 0.016 from our hydrometer reading of 1.250 for a corrected specific gravity of 1.234. In this example, the hydrometer reading is 1.240. The temperature of the electrolyte is 100 degrees Fahrenheit. We would need to add a specific gravity of 0.008 for a corrected specific gravity of 1.248. And as stated previously, a fully charged battery should have a specific gravity of 1.265. Here are a couple of examples of automotive hydrometers. They're simple devices that use a bulb and syringe to pull a sample portion of the liquid being measured up into the device. I think of it like a turkey baster. Some hydrometers use a needle gauge, like the example on the left. This particular gauge is temperature compensated and does not require interpretation. Other types of hydrometers, like the example on the right, use colorful and tiny floating pellets. If one single pellet were to float at the top while the others did not, this would indicate a 25% state of charge or 1.155 specific gravity. If 2 pellets were to float, that would indicate a 50% state of charge or 1.190 specific gravity. If 3 pellets were to float, it would indicate a 75% state of charge or a 1.225 specific gravity. And if all of the pellets were to float, that would indicate a 100% state of charge or 1.265 specific gravity. In this example, chart 50-1 displays a comparison showing the relationship between specific gravity, state of charge, and battery voltage. Figure 50.7 shows that as the battery becomes discharged, the specific gravity of the battery acid decreases. Figure 50.8 shows a typical charge indicator that can be found on one of 6 cells on some automotive batteries. A green dot would indicate 65% or above state of charge because the pellet or the ball is floating close to the top of the prism. If the specific gravity is low, in other words, the battery is discharged, or below 65%, the pellet or ball will drop away from the reflective prism, and the color you'll see in the window is very, very dark or black. If the sight glass is clear, that would indicate low electrolyte levels. I'm going to play a video produced by Shopware that can be found on the SMCC Library's Films on Demand. The video does a pretty good job summarizing how batteries are constructed and how they operate.
To make a fundamental battery, place dissimilar metals in a beaker of acid. One metal rod would form the negative electrode and the other the positive electrode. A potential difference or voltage will be formed across the two electrodes. The result would be a very basic battery cell. In a car battery, the plates or electrodes are flat to increase surface area and electrical power. Separators are used to keep the plates from shorting or touching. If a load is placed across the cell, voltage will force the electrons to flow through the load until the battery becomes discharged. Here we will show you how a battery is constructed. By removing the cover, you can see the compartments in the battery case or housing that form the cells. Battery housings are made out of a synthetic plastic material designed to resist acid corrosion, temperature change, vibration, and other forces. Each compartment in the housing holds one of the battery cells. The positive plates, separators, and negative plates slide down into the cell compartments of the case. This cutaway shows how an actual battery cell is made. Note how insulated separators separate the plates. The positive plates, the separators, and negative plates are sandwiched together. Each battery cell produces roughly 2.1 volts. Since modern car batteries normally have 6 cells, the battery is called a 12-volt battery. But more accurately, it produces 12.6 volts, 2.1 volts times 6 cells. Note the battery symbol in this starting circuit diagram. It connects to the starter solenoid. The ignition switch feeds current to the starter solenoid when the driver turns the ignition key to start. When the ignition key is turned all the way, a small current flows through the solenoid windings, ignition switch, powertrain control module or PCM, and back through the battery. This energizes the solenoid and closes its contacts. A very high current can then flow through the starter motor, the solenoid, and battery to crank the engine.
This concludes the Part 1 lecture for Chapter 50, Batteries. For additional information on this topic, please read this chapter and refer to the PowerPoint found in the Course Content folder. Now that you have completed this lecture and you have written down the online lecture attendance codes, please go to the assignment folder and take the online lecture attendance quiz in order to get credit for attending this lecture.